Do you have questions about what we talked this morning, just before the break?
Maybe there was a question in the back here that your question? Okay, that's fine.
Yeah. I will talk later.
Sure, okay. So now we are going to talk about the ways the models are inferred from what the system believes that temporal precedence means causality. Namely, it's about pattern extraction. So, this is being done by three processes called targeted pattern extractors that all work in parallel. We have three kinds. The first kind is called the change targeted pattern extractor. It's a process that is triggered by the observed change of a state that used to be consistent and is not anymore. Okay, say this blue thing is here and is being here for a while, and suddenly it moves. This is a sort of novelty the system will be informed about and react to. The second kind is called prediction targeted pattern extractors. Those guys are responsible for modeling the reason why predictions that were supposed to be true actually don't. In fact, they try to capture the reason why prediction fails. The last one, goal targeted pattern extractor, have the purpose to figure out why goals achieved are satisfied despite the fact that the system did not predict anything about it. So, as you can see on this picture, we have many instances of each kind. What does that mean for say, the first kind? We have as many PTPX as we have predictions. In fact, at any point in time, the system has made a set of predictions, and for each of those, a process will be instantiated trying to find out why such a prediction fails in case it does. Okay. Same goes for the GTPX. For each goal the system is currently pursuing, one GTPX will be instantiated trying to figure out why a goal is actually being satisfied despite the fact that the system had no models about it. So it is in fact another kind of novelty, you know. In the first kind, the system was pretty sure a prediction will come true, and it does not. So it breaks its assumption actually. And thus it will try to figure out why. In the second case, the system did not know how to achieve a certain state, and it observed that it can be achieved. So it has to learn why in order next to predict it. Okay? And so those are actually could be envisioned as top-down learning mechanisms. They depend, in fact, on the cognitive activity, the prediction and the goals. The last one can be seen as a bottom-up. Whether or not the system pays attention to a stable state, whenever such a stable state changes, this is also carrying some information. Okay. So the first two, and we'll see also the third one to some extent, they work quite in the same way. All right, so the raw inputs come in, as we have seen this morning, filtered by the autofocus, and this filtering depends on each prediction and goals. So I didn't draw the loop back here for clarity, but we know it exists. Okay, and all of those filtered in inputs here are actually duplicated here and here. What are those? Those are time-bounded buffers. They are circular buffers, the size of which is bounded by a certain amount of time. In the case of S1, this time was 5 seconds. Why 5? Because it corresponds actually to the short-term memory of a human. This can be thought of short-term memory actually. It's a subset of the big one, but still. So it means in fact that if after 5 seconds the prediction still holds, or actually is not broken, then the first entry here will be discarded and the whole stack shifted up to make room for the new entry. See? So in fact it means that if the prediction gets broken and the actual cause is last year, the system will never figure it out in one shot. What it will figure out is little by little, you know. It will figure out that this prediction did not come true because, say, of that thing here. Then this will become a new prediction. And we will need as many observables and lengths in time to go back little by little until the real cause is found 1 year ago. So it means in fact that if you are in a domain where the causation is a long hold, you know, the system will be quite slow to figure it out. But if it is the case, it might be a fundamental law of the domain, and then what you just have to do is to augment this. This size here is a parameter of the executive. Okay? Which of course can be changed dynamically too. Okay, so the same mechanism holds here and here. Okay. This I will talk about later, it's not important. Now, what is important is how does the system build up the models. So now I'm going to talk here in this slide as a case in point just about the prediction breaks. Okay. So say you have, and now I need to draw it. Okay. This is the time where a prediction P was generated. At this point in time, a TPX, this triggers the creation of a PTPX. The target is P. Right? Okay. And then from then on, you get inputs. Right. Say P is to be checked between T0 and T1. Right? This is T0. This is T1. Right? So, at the very latest, at this point in time, the monitor associated with P will check what we got here. And we could have gotten three sort of stuff. Either we have seen one, P, means in fact, success. Right? Predicted a P and I got one. Right on time. Just fine. The second case is I didn't see no P at all. Not a single P between here and here. Then I can surely access failure. Third, I see things like X, and where X is a counter evidence for P. Like, I expect this to be here, and what I see is this here. Not only don't I see this guy here, but in fact I see even worse. I see it somewhere else. A counter evidence. So this is also failure. Well, in the first case, I predicted P and I got P. Fine, I don't have to learn anything more. I don't have any more information about it. I predicted it. I knew. So here I don't do anything.
Maybe you could increase the confidence.
Yes, but this is not the role of the model acquisition. This is the role of the monitoring. That will pet the model and say, good boy. Okay. Now here, I thought I knew, but I was wrong. So the goal here, the idea, is to learn from the mistakes. Okay? So now, say here, I get a failure. It comes from here, or from there, or from both. Okay. So this has defeated my belief. Now, say the time horizon of the buffer associated to this guy here, say this time horizon is in fact spanning from, say, here to here. So those inputs here, I have forgotten about those. They are past my short-term memory, if you wish. Now, what will the system do, in essence, is that it will try for all of those guys here, for each of them, to build a tentative model of, say, this being the cause of that, and this being also a potential cause of this, and this as well, and this one, and this one. So just in abstracto, for simplicity, I have what? 1, 2, 3, 4, 5, 6, 7, 9, 10. I have, say, 13 possible models that I can build right now. 13. Just imagine I have 100, it's 100. For each failure, it could be a lot. This is not the most efficient way. So first, we have to remember that the whole system relies on try is say, for example, that this guy here, imagining this guy here, yes, here, is in fact the instance of a model, say, J, right? And this instance here, so J is something like A entails B, right? And here I had an A, right? So this A here had triggered the instantiation of this, creating a prediction of B, which is here, PB, but also the injection of the instantiation of this guy here. In this case, the heuristic goes as follows. I discard those. And I keep this. Why? Because by doing so, instead of having this entails the failure of P here, and PB entails the failure of P, and this, then I can simplify all of this thing and just keep the latter one, which in fact operationally includes those. So here I can prune things in this way. First thing. Second kind of pruning. Say I have lambda 1, lambda 2, 3, 4 here. See? Here. They are all within a short time window there. Instead of having lambda 1 entails the failure of P and so on, what I prefer to do is to notice that all of those are really close with regard to a tolerance of time here, and I will try again to hierarchize things. So first thing, I will create a state, a new state, S1, that says lambda 1, lambda 2, 3, and 4, and replace this by instance of the state 1 with the variables that I found here, entails the failure of P. One model instead of 4. Because again, this is a summary of those. Now, say I have a model state 2 composed of X, Y, Z. And here I find X, Y, Z, and here is the instance of S2. As we did here, these were the components of this. Here I do the same thing. I keep this, and I discard this. Again, the reason is identical. This summarizes this. Okay? So now, we are left with what? This guy here, that one here, that one, another one here, so on. Less, actually. Okay. Now, mistake. All right. Yeah. Okay. Then for each of the items in the pile that remains after the filtering, each of those will be used to build a separate model. So here in our case, 1, 2, 3, 4, 5, because this is a state 6 models here. So you see the thing is pretty greedy actually. And of course, among those 6, maybe only one or even none will be true. Yeah, because the actual cause might be here, see, and you don't know yet. So what I mean to say there is that we will get a lot of crap. That's why the process that revises the models is so important and must be given a very high priority in order to counterbalance the flooding by those guys. This is just a guess, you know. Okay. Okay. Yes, one last thing. For simplicity, I tend to represent a model like this, you know. Okay, this is only half of the truth. The true truth is a little bit more complicated. When we change forward, say I get an A where those guys are substituted by 1, 2, 3, right? This matches, so it means in fact that X is bound to 1, Y is bound to 2, Z is bound to 3. Good. And what I want to do is to create a prediction of an instance of B with what? X, okay, that's 1, Y, I don't know, and what is T, I don't know. What in heaven am I going to do with this? I can't check anything in the real world. A lot of things will actually match those. Those are wild cards. So, we have guards here that say things like W is X plus Z times 20. See? So it means in fact that those guards are meant to assign an actual value to something that otherwise would have not. So those here get a value, lambda and lambda prime. Now, this is good enough for forward chaining, but for backward chaining, we need the same sort of things. Because look at, suppose I get a goal B 1, 2, 3, means X is assigned to 1, W to 2, and T to 3. Now I want to produce a goal A with what? 1, I don't know. How do you think this will react when I talk to my arm and say, go to 1 here, and here I don't know, and there I don't know? It's not operational. So I also need here goals like these guys here to compute real values here for things who are not matched there in the same way. In fact, generally, but not always, it is the inverse. See? Like here, Z would be equal to W minus X divided by 20. Question, how are those guys learned. Okay, so what we have done is, say, remember here we had the failure of the prediction here, right? Prediction can easily be abstracted as, say, P, X, Y, Z, right? Good. And here, say, we believe the culprit is here. And this is an A of, say, X, T, R. So we will build a model just like this. That's good. But then we have to infer those guys here. What we have done is this. Each targeted pattern extractor has a list of equation patterns. Let me give you an example of what I mean by those guys here. One is this is just the prototype of a linear function. So, and from those, of course, we have the direct way. Say x means this, and the reciprocal as well here. And we have many of those guys here. It's called, in fact, a base of heuristics. The heuristics we have, where did we take them from? We just took them from basic geometry. You know, when you have a mobile that does this and bounce back here, you know, in the real world, in the real physical world, as we know it here, at least at the macroscopic level, it's always dealing with derivative about time, you know. So times the quantity here, plus an initial position here. Right, this is in fact this. It's the same thing. And we have a version with 2 parameters, 3 parameters, like here, 4, and so on, right? Thing is, we also know that by default, I didn't tell you that, but now I say, always the last 2 parameters are always timings. Those are the time intervals. So we already have yet another hint. All of those guys here are timings, the last 2. So when you deal with semantics like this, you know exactly where to look for. Of course, the real thing will not to do that. The real serious thing would be to learn the Hamiltonian of the system. This is really hard to do and really expensive. And to the best of my knowledge, only one guy knows how to do it now. It's Hod Lipson from Carnegie Mellon University, if I am not wrong. And he does it with a machine learning style, and it takes him years to figure out the Hamiltonian of a pendulum. You know, it's just a simple stuff. Huh? So don't take this as the silver bullet at all. Just imagine that this solves most of the toy examples we have been working on so far. One of the promising approach here is not to match equational patterns with observed real-valued relationship, but probably to do it in the north way, which means, in fact, that to learn it as we learn everything else. And in fact, to extract those equations from the models and turn them into bona fide models themselves. This, again, is just an intuition. It has not been demonstrated yet. But this, in my opinion, could be one way to do it cleanly. So I'm trying to be frank with you. I know it's not clean, but so far it helps a goddamn lot. Okay? So now you know everything. All right. Now I'm going to switch our attention to the goals. So the goal, so the GTPX works exactly as the PTPX, except for one thing. The trigger is not the failure, well, it is not the unpredicted failure of a prediction. The trigger is the unpredicted success of a goal. And the rest is exactly identical as what we just saw. Just the trigger changes. Just that. Now something else. So for the PTPX and goal TPX, what we get and what we need is for an event A. In the first case, we model the success, the failure, sorry, of a prediction, and in the second case, we model the success of a goal. That's all we need. But here, we want to model the change of a state. So the expected result is actually not the same. Let me call the state in question S. What I want to learn is when I have S, then when I get a condition C, then I get an S prime. In fact, if I write this cleanly, it is this. This is what I need. It's not one, but two models. Right? That's why the algorithm is not the same. Okay. What is the algorithm in this case? All right. At some point, I got to the state S. Here, I create immediately a change targeted pattern extractor that looked at S. Right? At some point here, get an S. Right? So this is killed, and I build a new one. Why do I build a new one? Because the timings are not the same. So it means, in fact, that some of the values here are not the same as here. And so on. And at some point here, I get an S prime, which is not S. This is my trigger here. All right. So now I will have to find in between this and that modulo the time horizon, same as for the other ones. So in fact it could be less. So here the possible causes. But that's a little bit more complicated. What is inside the buffer here? In the first case, it's really easy. I put in the buffer of this PTPX here all the inputs I paid attention to. See here? Only the things that are relevant to P I'll put here. Is the role of that guy here. I mentioned this morning that the relevancy of an input with regards to, say, a prediction is defined as an input is relevant if it shares at least one value with the target here. Right? Okay. Same here. Okay. But here, not necessarily. That's why we will use as the buffer for this guy the union of all of those. Why do I do that? Why not, for example, shan't I just simply say, okay, fine, I define the relevant inputs here the same way as there. Namely, the inputs here are only the inputs that share at least one value with the state here. Which one? This one or that one? First question. And second question, those guys are defined as such because prediction and goals are what the system semantically is really interested in. The system is not interested specifically to any change. But we want it nevertheless to be aware of it. Right? So for a practical reason, this one or that one, and for a more theoretical one, a change is not an activity of the system, then we have elected to use the union of all of those guys, and that's what we call the cross buffer here. So this is the second change in the algorithm with regards to those two guys here. But after that, we have the same way of filtering things. It means that first, we will try to retain only the instances of the model that fired instead of the components of the firing. Second, we will retain the instances of composite state instead of their components. Again, for the same rationale, to try to hierarchize as soon as we can. So, first we will build this with the same algorithm that we used to build those guys. Right? We have a target here, right? And one possible cause. So the algorithm can be reused, no problem. What changes is now how to build this. This is just an addition to the algorithm of the first case here. Well, now that we have this, we also build that from an instance of C and from an instance of S prime, right? So I get the values here and here. I just built a model of it here. So I observed the first occurrence of that guy. So I will create it. I also have an instance of S. It was actually the event that triggered the creation of the targeted pattern extractor here. So I also have S. Right? So this I have used to abstract them into this guy here. And now I have this that can be abstracted into S, and this that can be abstracted into this. Well, with the same algorithm as this one, I can assemble this into M1. Right? Now, there is a last complication, but I won't delve into this. It might turn out that this guy here, S priming, is actually for the variable x, y, z, t, r, right? C depends actually on, say, x and z, right? And S is actually x, y, t, r. We have seen in the preceding case that we have found a simple way to identify and relate words in between two terms in the same box. But now we have this guy that can depend on that guy here. Means in fact that I have to pass some variables from this to here in a special slot here that can be used here. The same way the variables here are being used here in the general case. Well, you will see if you're interested in the replicode language specification, all the models and states have a list of what we call template parameters, just as we use in lambda calculus to propagate the continuation of the calculus. It's the exact same way. Bon, that's rather technical stuff. Just to tell you that the goals can span more than the scope of a model, actually. Right? Okay. So, regardless of the source, this one, that one, or that one, you now know that all of those activities are all done concurrently, right? It means, in fact, that at some point in time, you may have this. Here, model M. It says A entities B has been doomed like a very, very bad guy and being killed. Right? In the same time, there is a TPX here that reaches target, say here, target, and then creates here this guy, and prime, and tells B. And between this and this, there is an epsilon. to see the problem that we might have here. We might see things periodically that look good but aren't good, that were used to predict things that turn out to be false here, triggering the same model based on a recurrent irrelevant thing, A. And this can happen quite often, actually, right? And we might have the opposite, you know, here. Here, I create, so here, yes, I create a new M first. Yep. And here, I kill M with an epsilon prime here. Well, so the current implementation is this. And I tell you in advance, it will not last for long because we have found a workaround. But anyway, in the current state of the implementation, before we create a model, we check two lists. A white list and a black list. The white list is the list of all the models that so far are well behaved. Because look, in the primary group here, I might have had in the past a model M here, which is not there anymore, right? Because the context has changed, but M is still here. Now the context is changing. And M was, say, A times B. And this context is back again. And so I wanted a B. I don't predict it because M is cast out, right? And I see an A. And what will I do? I will try to explain this. And I will be right, in fact, in doing so. So I will say, hey, man, I found this. So then I will have this. And the next time, this guy will have predicted well too, and will be switched back. And then I will have two identical stuff here. That's why we will check the whitelist here. And if a newly proposed model matches an old one, we don't inject it. And for the first case here, we will check the blacklist. This, for example, will be stored here. And then if, in this case, I want to do that, I will find that this entire thing here matches this one. So I will refrain from injecting it. Okay, theoretically, it is good. In practice, it's not good. Why? Because all of those typics are meant to operate concurrently. But why do I do by checking here? I have to put a lock. This timetable is accessed concurrently. So it defeats the purpose in terms of execution. So now we have thought of a workaround that actually what we will do is first is to avoid this here and here. This will be done by reshaping the scheduler. So it is easy. And this here will have those guys predict first. What do I mean by first? Not by putting yet another lock, no, but to take the prediction of this guy and put them directly in the buffer of the TPX. And since a TPX is invalidated when an event has been predicted, then he won't do that anyway. Okay. Yeah, we have also some rules that helps pruning the buffers, but it's not important. Just keep in mind that the most important rules for trimming the buffers are the ones that aim at hierarchizing things. Do you have questions about that?
So I see this thing working well if you take like the short-term memory thing.
Yeah.
But if you want to do it, let's say, in a longer time horizon.
Yeah.
Do this, because then you will have a lot of possible causes and effect relationships. Say, I see that something happens today because I did something yesterday or something like that.
Yeah.
So how does it deal with more long? I mean, for language, it's real-time more better.
So, the long and short is this. In your example, this event happens now because you did that 3 days ago. Okay. How is it in the hell that you remember this event 3 days ago? Why? That one in particular and not some other ones. And for sure you don't remember now whatever you did or happened to you from 3 days ago to now. There is even things that happened to you 5 minutes ago you don't remember. How is it that you remember specifically for that case that it was related to what happened to you 3 days ago? It means in fact that you now pay attention to what you did 3 days ago because you believe it's related to what you are focusing on right now. Okay? Well, and there is many ways actually to actually explain this. The first and easiest is that in fact is not really because of one thing that you did yesterday, but yesterday was the trigger of a chain of events. Like A, and then B, and then C, and then D, and then E, and then puff, big deal. And this is now, this is this morning, and this is yesterday. Well, then you know, this will be used first, then this, and so on. Okay. And this is already handled well by the system I presented, no need to change anything. But now, what if actually it was this? And this is 1 year ago. You know? I pressed the red button 1 year ago, and today the doomsday machine finally works. Well, here I don't have any answer. In order to pay attention to that and to recall that this might have been the cause, it must be in that very simple example that you know that red buttons generally cause strange things. It means in fact that a lot of your past experience would be summoned in order to imagine things here. Like when I press the red button, the control bars of the atomic nuclear plant, they get up, then the thing hits, then the cement melts, then you have a Chernobyl here. But this is that what you imagine, because of then, that you have read things, you have been told things. In other words, you got some kind of experience about it. But as the system is now, it doesn't do it automatically at all. It can do this and only this, you know. In future version, as asked this morning just before lunch, the system will be equipped with ways to imagine some of those things. And I just say some of, you know, and probably not all. Because, you know, in the real world, the knowledge doesn't go full-shaped in one go. It's always incremental, actually. So this done, this not. This depends, in fact, on the amount of the little hints that you get here.
Do you have a theory how memory is stored? Say, I will use human as an example in this case. Say how memory is stored in human brain, and whether it's related to the pattern recognition.
What is the question?
How memory is stored. Say you remember a person, but every time you see this person, it's different. Like from a different angle or with a different shirt or things like that. But you can always recognize this person.
Yeah.
So so how is this memory of this person stored? And then also about this event, how are they stored, if they are stored at all in our brain? And then how do we access it?
Yes.
Whether there is any analogy between the human memory and the AERA approach.
I'm going to be disappointing here. I'm an engineer, I'm not a physician, you know. You should ask a neuroscientist, and well, I'm not even sure. I don't think they actually know, in fact. I don't think nobody really knows.
I think you'll get a pretty good answer to that question if you read the past, say, 7 years of publications on that subject in psychology and neuroscience. But that's really the only way to do it, because either one is fairly limited when read alone. But I think generally, though, that would tell you the state of the art. But I think generally, Eric is right in that it's not very well known yet. I mean, rough outlines are starting to emerge and have been emerging for, well, since computer science started doing this, maybe 70s or so. But
yes, I was also thinking about that question. About this sequence of events, and you have to store it somewhere in order for you to retrieve them.
Yep, right.
And then if you store them, and then what structure you store them? Like is it in a graph? So when you retrieve, you can send out to every single other event in the past, or is it like a sequence? So you go back.
Okay. Yes. Okay. So. Okay, how to present that? The simplified version is this. Buffer here, so it's a circular one, okay? Which is limited in time by a system parameter called the time horizon. Right? So it's a mere stack, which is, well, which in fact trades on itself. Okay. This is how I presented it, and this is what it's enough for you to know. But the real true truth is more complicated than that. Because I didn't go into detail of the language we have developed to implement all of that, you know. But in our system, yeah, and knowledge is like this. Damn it. And you also have, yes, and you also have this. So, nodes that are arranged in a graph that points to some nodes or to edges, and an edge is also a node. And all of those have a saliency, you know. So some of them are more salient than others. And when you start to touch, say, this one, then you propagate some of the activation, some of the saliency to the neighbors here, that propagate a little bit less to this guy here, and even with a built-in mechanism to prevent the looping back. In the fashion of activation spreading, except that it is not activation here, is the saliency. And we do the same for the models, and then it's the real activation. So yeah, but this is really deep in the guts of the language, you know. At the architecture, well, of course I know it works in this way, so I know that by doing this it's enough. Because, so here we have each one node here, you see? It can be this first, and that one here, and some other here. And when I touch this spreads.
So you're using like pointers, right?
Yeah.
But then do you update the link between them, like dynamically?
Of course. Yes, of course, it's the point. Yes. Yes, so yeah, you have a state here. Composite state. Built of X, Y, Z. It's a node each, you know. So it means, in fact, that when I want an S, I will make those guys, and those are patterns. Huh? We'll look for X, Y, and Z. And maybe more X, because I have seen more X in the past. And Z's, you know, they are here once in a while. So if I don't see Z, well, I don't really care, provided that I have enough strength here and here to then infer S. Okay. Reciprocally, when I see an instance of X and an instance of Y, an instance of Z, here I can go back here and say, aha, I have an S. And those guys have been learned in, like I have shown there. Same when I have A entails B, you know, but you have this, in fact. A and B. And more than that, I can also, you know, yes, the language is in fact more rich than just state and models, actually. You can really express things. The man who was in the forest and saw the bear that was born. So it's endless, actually. But in the end, it's like this, internally. But this is not even part of the architecture, it's part of the executive. It's really right in C++, you know, and you can't change that. It's, yeah.
But that's very important, isn't it?
It's helpful, yeah.
In fact, the key feature of human memory historically has been the associationist perspective, which is one memory triggers another memory, etc. And this seems to be at least one of the top 2 or 5 main features of human memory, how that works. And that's why, you know, for example, mnemonics, when you try tricks to remember things, if you don't remember the name of something, I don't know if you used this trick, I use it sometimes, you go through the alphabet and then a letter will trigger, oh yeah, I know, and now I remember his name. Or her. And this is by, it's an associated, it seems to be at least in some fundamental way of an associationist network.
Yeah, but that is not how neurons work. Is it like
Oh, there's a lot of ways.
Well, that's what they say, but
But the problem is
we
as
don't
far
really know.
as I know, there is no very good knowledge of how the neurons or neuron clusters relate to
Yeah.
psychological phenomena.
That's it.
As of yet. This is the main problem.
Yes. Yeah.
And I guess by now people probably have some good ideas. But still, the neurons are at such a low level of detail, it's almost like studying not maybe a skyscraper, but a big house by looking at the grains of sand. And of course it's very hard to see, oh, I'm studying now the windows, if all you have is grains of sand. And you know, current models of neurons have maybe 100 or 1,000, 100,000 maybe, in that range of neurons modeled at a reasonable level of detail. That's tiny compared to the brain and compared to the psychological associations that you get. You know, I remember my grandmother. You know, it's just.
Thank you.
Okay. Okay, so now I'm going to present something which is not finished yet. Okay, so compression. Compression is required for scalability. We need the system when it knows things well enough to be able to compress abduction paths into one box instead of a string of boxes. This saves the memory. This saves the maintenance. We don't have to evaluate those and rate those models again and again. It saves also on the simulation part. When you know how to work, you don't compute the possible effects of putting your foot somewhere. And last, it improves the execution performance because C++ code, of course, is faster than interpreted one. Okay. So first, what do we want? We want first to identify and encode in C++ a plan. What is a plan? A plan is not a list of action. It is not this. If you do that, you shoot yourself in the foot. A plan is a list of sub-goals. Because if you say a plan is a list of action, you prevent the system to learn better ways to implement those actions. And you will stuck the system in old habits. What you want, in fact, is to have just a sequence of things to be done. The best way the system can do them as it accumulates more experience. So what we expect as a first stage of the compression is one goal and a list of the sub-goals that we have learned are needed to achieve the main goal. Okay?
Why do you use for a list of goals and sub-goals C++ and not just some script, some scenario? Is it declarative knowledge or is it imperative? Because if you need the programming language, then it is imperative. And you just said that you don't want bad habits for the system.
Yes, yes. But this is not the only reason. The next reason comes on the next slide, but since we're at it. Okay, look, here we have one abductive path, you know, the red one. So it's nice. We would like to say, you know, we see in many cases when this chain is the best one. Okay, so what I would like is to take all of those and replace it by one black box, you know, solid, good, honest C++ code. But let's not forget that those guys are also needed to predict things. Say I brutally compress those three guys into one box that just do the sub-goaling part. But I will lose the former ability of the system, say, from here to predict things that might be of interest of this guy here. So at first, the objectives might seem contradictory. I want to kill everybody to replace by one dumb thing while retaining the plasticity of, well, okay. But when we think about how it can be done in C++, you know, it's not hard actually. It's not hard at all. So let's forget the predictive part for one moment. What would be the way to implement this in C++? It's really easy. You match one goal here. The matching API of the executive is available, so it's just a function call. Fine. Then just a stack of goals that all points to the values bound to the variables of this guy here. Okay, and in a timely fashion, well, you inject each member of that list at the due time, right? Just by doing this, you already gain a lot. First, you suppress the need to simulate here, here, and here. First thing. The second thing, you have you don't have to evaluate backward this one, then that one, then that one. What you have to do now is just to evaluate the first end here and just lock all of your items in the list on a timer. That's all. So just that, you save a lot of time, right? Now, we remember the discussion about rendering the functional service of predictivity in the other way around. Well, in the same way, we just don't maintain a list of goals to be issued on certain moments in time, but we also have a list of predictions done in the same way, all locked on timers. So the C++ code actually that would implement this is pretty short and easy. But now, this is just the gist of it, but there is a lot of problems that must be investigated first, because we, of course, have some cases. So, before getting into the difficulties, let me say a word about how do we right now identify the right ones to be compressed. Why those three guys or four, and why not those? Okay. Well, actually, this comes for free because we use the exact same learning mechanisms as the one I presented a few minutes ago. The only thing that changes is the semantics of the inputs. What we have seen first is when I see a mouse here, then I see a cat, then the mouse runs. Okay, those are inputs that come from the exterior. They are coming from the world. But let's not forget that each time a model fires, we inject into ourselves the instance of the firing. It means, in fact, that what can be also predicted is when this guy outputs a goal, then this guy also outputs a goal. Or, symmetrically, when that guy predicts things, and when that guy predicts a thing with the same input, it always fails. It means that those are not a good path. But those always work. So based on the chain of this works fine implies, or more exactly entails, that this will work fine, and this will work fine, and the super goal will be achieved, and this is learned the exact same way. Just that we will have IM0 entails IM1 and so on. Just as we did in S1 with words. But no, it's not about words, it's about the models themselves.
Is the pathway revisable with form?
Of course, yes. Because the success of this entailing the success of that might be observed for a while, and again on Monday it's not true anymore. So those will, so the models that captures the coupling here will be phased out. But except on Monday it will be phased in. And after long enough of this, the strength and the confidence on that link will be strong enough for the system to say, hey dude, I can compress this. And assign to the whole thing the success rate of the model that captured the coupling. So it means in fact that if that, so this until this is not valid on Mondays, it will be the same thing for the collection. So it means in fact that at this time, this black box here will be seen just as a single model that will be also phased in or out. Okay? So this is the idea. But of course, there is some trouble. Because if I identify this as being a good target for compression, it turns out that this was useful to achieve that. So if I replace this by one single piece here, you know, the pattern of this guy here is the pattern of that guy, not of that guy, and not of this guy either. So it means in fact that here I break chains. Right? So this, in fact, technically can be easily detected, because since we are able to learn the coupling between things here, right? But we are also able in the exact same way to learn the coupling here and here. And when we see an intersection of this guy, which is coupled to a candidate for compression and also coupled to something which is not a candidate for compression, what we would do is we will compress anyway, but still we will have those two guys stay alive in the background until eventually they get compressed themselves, in case we finally get enough knowledge about that part. It might come true or not, but since we don't know in advance, we don't have the the choice actually, and we will accept redundancy here and here. So yes, another issue at hand is what if the world dramatically changes? It means in fact that to compress things into C++ is not reversible. Why? Because we will have lost all the intermediate patterns, and it will be really hard to reinforce them. So in fact, what we do whenever we want to compress a set of models, we store the original on disk. And when, if by chance, the compressed version of things is becoming to behave so badly that it will be killed, then we will swap back the original ones, and we will put them back in place. And maybe it will turn out that the culprit was just that guy here, but those guys are completely fine. So this would be the way to regain the plasticity that we have lost here. Yes, and last one thing, we don't need to compress things while we are on the job, you know. You can think of it like a form of dreaming, actually. It's garbage collection, you know. So this sort of activity is only done when we don't have anything else to pay attention to. In fact, it can be done completely offline. And that will be it before we get into the concrete example. So, do you have questions about?
What does the last sentence on the last slide? Compression is performed during periods of inactivity.
Yeah.
That means when the system is idle,
Yes.
it has an extra time.
Yes.
Fucking working.
Right.
That's why.
Yep.
They're like human beings. We will
Sort of, yeah.
reflect upon our methodology when we are idle.
Yeah.
But you could also reserve some percentage of the CPU,
Yeah.
so you could do this always on the fly.
Yeah, yeah.
But that would mean, you know, you might have less CPU for other things.
Yes, right.
Well, actually, it should be the right way. In fact, this is done exactly like the normal learning, and we have been pestering everybody since 5 hours to tell them it's incremental, right? So it could be done also incremental. Why? Because the mechanism is the same. So if I have 1 minute when I don't have anything, I can look back and learn a little bit, and make a candidate, and soon then with an alarm, okay, fine, I remember it, but I'm going back on my job, you know, and so on and so forth. It doesn't have to be sharp and coarse grain.
So to take an analogy, the machine learning community says, oh, we can make learning machines, but they will have to sleep for, you know, hundreds of hours before they can do anything useful. We go the other way. We say we want the machine that never has to sleep, because it's easier to go back and say, okay, well, let's give it some time to rest. You know, let's give it some idle time. But it's very hard to say with a machine you've built that must rest for that must think for hundreds of hours before it's useful. It's very hard to say about that machine. Okay, now let's make it completely not need that kind of a period.
Another is if the user wants or expects the system to get the compression job done, they will offer inputs. So implicit patterns already.
Yep. This is really interesting, and we are only trying to, well, we are only getting there. It's related to the developmental aspect of the thing. When you create the little seed, well, the first egg of the chicken, which is us, okay, chicken and not egg. Well, the best way to train the machine is to give it regularity enough so what it sees in general is not crap or less crap. The worst is to show the full complexity of the world to an infant. It will get completely insane. It's too much at one point in time with regard to the thickness of the knowledge it already has, and it's in infancy is really small, you know. So a good attitude would be for the teacher to present things which have the less complexity first and the most regularity first, then to ensure this is well learned, let the system be completely idle and don't ask it anything for a minute or an hour, whatever it takes, so it has time to compile, freeze the CPU to learn more complicated stuff, you know. But this is not, it's not in the architecture actually. It's some hints that we are currently trying to think about is the methodology to use this sort of architecture in a long-term developmental approach. Yeah.
Mm-hmm. What about interpreting the things that machine did learn? Chris was talking about it, and I was just wondering, how do you see it? How it would be done in general?
How would be done what? I didn't get the first part.
Machine will be learning some knowledge.
Yeah.
And if we want to see what knowledge had it learned,
yeah,
for us.
Yeah.
What will be this process look like?
Okay, but well, in the long run, I don't know. But what we have done so far is this. Well, in S1 in particular, at some point, you know, after a series of training sessions, we stopped the machine. Well, we stopped giving the machine an input, and we just input some goals that we were expecting it to be able to solve. So it was in fact not like those metaphors, but it's a sort of exam, you know. So say I expect the machine to learn that A entails B, entails C, entails D, and I want to check if this has been learned. Well, I ask it to solve D, and if eventually it gives me an A, fine. See? That is the way that we use now. I'm not saying it's the best way, because it's tricky. But we still have to work on the, yes, absolutely, on the benchmarking and on the teaching and the driving on also. Because it's easy to see that we might start by teaching well, you know, and the knowledge goes up and is useful, and at some point we don't know at which point in complexity the thing will still be able to learn interesting stuff, or if the teacher will make so many mistakes that the models will be crap, and the thing will start to collapse. And we don't know that, you know, yet. So it's not only about the architecture, it's only research about how to use it and drive it in the productive way. But we are just in the first real prototype, you know, so we'll have to wait a few years to know more about that. Yeah.
Well, another short question. You have mentioned how to compress production and deduction pathways.
Yeah.
So what about induction? You have mentioned it?
Yes, what I call induction in in here is the extraction of patterns. It's the building of models.
No? Just the pattern.
Yes. Yes, and
attraction.
yes, and those of course are not compressed at all. They are not part of the memory actually. So
yes.
yeah.
Can a compression be hierarchical, like the models?
Well, yes, it is. Of course, it is. Well, actually, we don't have the choice, you know. Generally, you know, the more stable stuff will be higher in abstraction because they are more general, so they will apply to most cases. So individually, those guys here high in the hierarchy are likely to be more stable than the little excited ones here that react at a microsec, you know, and sometimes they are wrong. And okay, but the trouble is that those guys are so general that they might serve this and 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 this. All right. So paradoxically, in the few experiments that we have done so far on S1, is that even if those are quite unstable compared to those links here are more stable than those. So so it turned out, but this is just experimental. It's not theoretical at all. I cannot prove it. But I have seen it twice actually. Well, we have made only 2 experiments there that we actually start to compile from bottom upwards. Intuitively, it looks like the system learns these basic reflexes, you see.
Like the goal composition.
Yep, absolutely. Yep. Yes, and of course, since this becomes one box, then you can compress this, and you have a black box that calls, in fact, a sub-black box. It's just a C++ fun call. So in this sense, yes, it's hierarchical, of course. Are we good? Okay, then let's have a break. Now we are going to use an example to illustrate what we have been talking about this morning, and I mean by that the execution of the model hierarchy. It is not a question here to delve into how the models are learned or rated or phased in or out. We don't care about that. We just want here to get a concrete grasp of how the chaining forward and backward is actually used. Okay. So it's a simple example, you know, it's just a robotic arm that holds a thing here. And we give it the goal to put that thing there. And it has one hand only. It can't do that, you know. So what we expect is the thing that does this and this. Right? Okay. So, yeah. So, the effectors are move the hand somewhere, grab and release. That's all. What is the hand-coded ontology that we give up front to the system is that the system will be able to, well, the drivers actually will tell the system that this is blue, this is white, this is a sphere, and this is a cube. Okay. And this is the position of an object, and when it's like this, it is attached. It's the only thing. What are the inputs from the environment? Is the position of the things of interest, the events when a thing is attached or not, and the efferent copies. What do I mean by this term here? Yeah. This is the environment here, And say here you have now your device driver. Let's just imagine you have a model here that says A and says B, right? And let's imagine also that this driver here has one command which is matched by A, right? Okay. Now I have a goal here that wants B. Then logically I will output here a sub-goal A. The goal A matches the command here, so this will do A in the environment and change things here, and in response we will get some reaction here. Right? Okay. So this is the simple case. I want to do A and I actually do A. But say this is move my hand, right? And with the guards here and the goal here, right? Say I have a goal that says I want my hand to be there, right? With a model like this, I will ask my arms to extend there. And of course I will fail because I'm too short, you know, I can't get there. But I need to know that I didn't get there. I need to know what is the real command that I did, you know. So what is expected, and this is part of the API of the device driver here, is when we get a command here, we re-inject an efferent copy, which means in fact the actual command that was actually executed. This is useful because, for example, it allows the system to model this. Now I am an adult and I know that when I want my wrist to be there, I will fail, and I know why. Because it's too far, or because my reach is limited. I have acquired a model of this thing. And if I didn't have that, I couldn't predict that I will fail. So I will try to do it again. And I will be ridiculous for the rest of my life. Okay? This is one thing. It's also useful to model in the exact same way this sort of IO device when there are a sensor. Because the sensor in the real world, they never work right. They always have faults, or they degrade over time, or the context is a little bit unforeseen, and suddenly the camera is not as good as it used to be, you know. I need to model this. If this is a way to stir the head, right, I need to know that in some context I will fail, that the command that I send here will not be executed as I expect to. And I need to model it in order not to issue such a command because it will not work. Okay, so this is a key requirement. It is not part of the architecture, but it's a requirement on those guys here. Okay? So I will assume that in this example, all of those guys here, whenever they get a command, they re-inject the command that has been actually executed. Okay? So yeah.
Could you say something more about the ontology sense? Is this part ontology sense is
yeah.
It just tells us the ontological picture of different things.
Yes, it means in fact that here you can imagine, say, a vision system, right, that will tell me here, this thing here X. So X is a cube.
Yeah, it's a cube.
Right? Oh, I forgot one, the color too, you know? Or X has the color blue. Or X is at X, Y, Z. You see? This is, so those are ontological relationships that we will expect the interface to give us, right? In the current state of affairs, the architecture as of today is incapable of creating those. So it's not nice, but it is the true truth. Well, soon it will change, but now it can't. So, okay. Yep. So, now I will give the states and models that will form the knowledge given to the system before we give him the goal to grab some cube and put it somewhere else. Okay. So this is of course pseudocode because the replicate syntax is quite lengthy. So for the sake of concision, I write it in this way. All right. So first, this is a composite state, right? It means that something that is a variable h doesn't mean anything, just something. Okay, is a kind of things x, and this holds in between this time and that time. Okay, the same thing I referred here to occupies a location in the space called P, somewhere between the same time values here. Okay. All right. Yeah. Then, first model M0 here. Okay. This is a command, just as this case here. See. Using the fact that instead of A you have move, and it's in fact an entry point move in a device driver here. It's identified by this keyword here. Okay? And those are the arguments of this guy here. So you move something by vector here. Okay? So it means in fact that when I move this thing by this offset between this time and that time, then it will entail that that very same thing will be at a position like this between that time and that time. But you see here, T1 and T1 can be found here. So that's enough, but T3 is not there. So if I didn't have guards, I will predict a non-defined thing, which will be very hard to check against reality. So I won't be able to rate this model, and it will stay there forever, even if it is wrong. So we always, in cases like that, we always have guards. This is one instance of the linear function I gave the template of a few minutes ago. So it means, in fact, that the final position is the initial one plus the offset. You know, simple linear stuff. Okay. And as far as the timing is concerned, yes, we will assume in this example that this guy here is at a fixed sample rate. It means, in fact, that it gives you this sort of infos every, what is the sampling period? every 100 millisec. Okay. So this is used to evaluate those guys here while chaining forward, and we have the inverse, in fact, when we chain backwards. Okay. All right, so this was for M0. Now we have M1. M1 is, in fact, precondition on this guy here, and we can see it because of this, right? Okay, it means, in fact, that if we observe a state like this, right, then if this guy predicts something, it will be right in doing so. Okay? Why do we need that? Because look, this is a change in the position here. See? The position is here, right? And here, where do I get this guy here? When I read the left term, I don't see any position at all here, right? The right term, I don't see it either. It's not there. It is, in fact, in the template parameters I mentioned, you know, the lambda thing. This is placeholders, actually, to propagate the binding of variables across models. From here, it jumps here, and is subsequently used inside this guy, actually here. Right? We have seen, at least in principle, an example of that when we were talking about the CTPX. The parameters, well, the variables of the state, of the initial version of the state, were propagated to the model that explained the cause for the change of that state. All right.
These two, are they drivers or this is not drivers?
Not drivers at all. This, in fact, could have been learned. It's what we would call, well, at least in the field, motor babbling. Just like a hysterical little baby, you know, I do that. Oh, it moves. Oh, it moves again. But learn things, yeah. It is not a drive. The drive is, in fact, is the definition of what the client wants the machine to do, and tells the machine, I paid your creator for you to be my goddamn slave, and you are going to do it. It's not paid to learn, actually. It's paid to be on the job. And this is the function of a drive. Yep. Now, more composite states. What is S3? So S3 is basically, well, in fact, it says, well, it's almost like this one here. No? A thing of a certain kind occupies a location P here. And what is S1? S1 means when one thing is at a position P, when another thing, this is not the same, huh? Another thing is at the same place as the first one, and those two guys are not attached. It means, in fact, this. And no handing is attaching it.
No one can see that example.
Oh, true. It's like this. Well, yes, but then my hand is attached. Voilà. Okay. See? All right. Yeah. So now, this will be used later on. Well, here actually. Now, this is a model that describes the consequences of grabbing things. you know. When the hand is asked to grab whatever, you know, say you ask here the hand to do this. Two cases it's empty, or there was that here, right? Well, then whatever is here would be attached to that hand. Here, same. We have a precondition on that. This will work if and only if. So something will be attached to the hand if it is at the same place as hand and it is not already attached. See? So do you follow what I'm saying here? We can imagine really easily how this has been learned. Look, so at some point the machine had the goal to grab one thing. What would be such a goal? I want something to be attached to my hand. The goal would be there. And it doesn't have this guy here. So it does not now. But just imagine, by doing this motor babbling, and it grabs, puff, it works. Then it will say, going backward from the unpredicted success of that goal, go to the events, and we'll find at some point in the in the buffer of the GTPX that this thing and that thing, first thing was not attached and were at the same place. Buffer would have been trimmed according to the rule I presented. We removed the components and we built the composite state. This one, right? Okay, so we would identify that this is a precondition for that. So I do it again. First, the goal is here. The first thing I see in the buffer is I did grab. So first I build this. All right, and I do it again. And if it's still there, it works, and it works fine. But at some point, I do it again, and this is not there anymore. So the prediction here will fail unexpectedly. Then the TPX kicks in and tries to explain the failure of that. What would be the case when this fails is when things are not in the same place or are already attached. The negation of a negation is nothing more. So here, you would build this, in fact. Okay? Okay, so this state is easy to read. H and C are at the same place, and they are already attached. Okay? Same thing when I release my hand, things are not attached anymore, and I have seen that on one example. And on the next one, it fails. So my prediction fails, so I have to explain it, and I explain it by having this here, exactly in the same way that we have seen with grab. The only thing that changes this term here and that thing here. Okay? Okay, some more interesting stuff here. What does M6 say? M0, remind you, means that when I move the hand by a certain offset, the final position of the hand will be the initial position plus the offset. Okay. And the final position is actually, there is a bug here, it's not C. It should be P1. So yes, it is a bug. P1 here. Okay. So it means what? It means that when the model M0 fires the prediction of the next position of the hand, right? Something C here, which is in template parameters, will also be at the same place. And what is the precondition for that? Precondition, you can find it here, is those two things are already attached. It means, in fact, what? So this means when something is attached to the hand, and the hand moves there, then that thing will also be there. See, it's a reuse of M0, and we don't have to infer a model of the displacement of this thing. We reuse the conclusion of this guy here. Okay, this is in fact a post condition. Okay, and that's all that we give to the system until we eventually give it the goal is to have this thing it didn't have, you know, and put it there. Okay. So those are the initial conditions. It means that those are the first inputs that the system gets from the moment it is start on. Okay. And now we will have to use those plus this and chain in all the models that we have seen and see how things work. Okay? Okay, so what can we do with those things here? Those are mere inputs actually. So at most they can trigger forward chaining. If we go back the models that we have, well, we will have this guy matched. Huh? So the hand is here. So this matches, but this is just a state, you know. Do we have a command? No, it's not in the list of the initial thing that we have, so this will not fire. We will have this. Since we have an instance of this, we will predict that if we had a move, then the hand would be there. But only if. But since we don't have a move, this will not fire at all. So on that front, everything is quiet. Here is the same thing, you know. This is only a precondition that controls the execution of a model here that can be triggered only by a command, but we have none of those yet. So this will remain silent. Same here, for the same reason. And same here, because we don't have an execution of M0, so this input will not be seen. So this guy will not want to fire anything, right? So this, which control the execution of that only if this runs, will not be used in effect. So the impact of the initial conditions that we have seen here is nothing. Now the last input that we have now is that one. And this might change things. Okay. So this, at most, can trigger backward chaining. So now we have to look at a possible match of this with the right-hand side of the models. Okay? All right. Okay, so the goal is what was the goal? I forgot. Oh yes, yes. So we want an entity S to be at a certain location here. Okay. And it turns out that this actually matches this here, right? So we simulate stuff. So I pass you the details of simulation. Let's just assume that there is no conflicting goals here, right? Okay. So I'm tempted to issue a command move on the object S, and S is this. Huh? Bon. Right. So so what will the executive do? Say, before I output things here, I check if I have preconditions. Do I have some? Yes, sure, here. Right? So before sending this goal here, we will check if this precondition is met or not. Well, actually, it's not. We do not have an instance of a zero with instead of the hand here, the thing that we want to move. This was in fact actually designed to prevent the execution of this on something else than the hand here, right? Because we know that our device driver controls that hand and not things. So far this will not do anything wrong here. Let's examine some other things that we have. So the desired fact about the position will not match this, of course. So this is not even considered. For the same reason, the release model will not be summoned. Aha! Here we have another candidate here. C matches S. This, remember, is a bug. Huh? So P1 here matches PS1, the desired position. So here, before issuing this sub-goal here, I will have to ensure this precondition is met, right? Is this met? Let's see if we have actually an instance of S2. What is S2? S2 is this. Is that the hand is at some place, right? And something else is at the same place as the hand, and both are attached. And this is actually true because the hand is currently holding this. But the fact is, it's not this. So what I want actually is not what I currently have. So what the backward chaining will do is, first I need this. In order to have this, I need this. With hand, the position where I want, well, the position where the hand is, and C is not this, but this. So now I will output a goal, G1, which is in fact ICST of the hand. The position of the hand is pH0, if I remember correctly, and the sphere. I save you the trouble of computing the timings. Okay. Right. So this is what I want now. Oh yes, I forgot the name of the state. And S2, we remember it is in fact the state of having two things attached. So what does the executive do when I got a goal like this? Didn't tell you in the theoretical part, but this guy is also capable of backward chaining. Okay. So now what I have, so what the reality says right now is that the hand is at the position pH 0. The sphere is at the position PS 0, and the hand is attached to the cube. That's the current state of the world. And what I want is the hand is at a certain position P here, there. So this is good enough. The sphere should be at the same position P. This is not good because this is not this, right? So here I will create a sub-goal G2 that would say the sphere should be at the position pH0. And I also want here the hand attached to the sphere, which is not the case here. So this will give me a goal, G3, hand attached to sphere. Right? Remember, those are instantiated by virtue of pattern matching. It means, in fact, that every valid combination will give birth to an instance of S2. Here, you see, I have used the instantiation in that order. What if I had matched it in this way? First, I match this here, right? So it means, in fact, that P becomes bound, so P becomes PS0. Whereas here, P was bound to pH0, right? Then this would not be checked because the hand is not at the same place as this guy here. So I will have goal G4, hand at the position PS0, and here would be the same. I would have G5, hand attached to S. Here I have two goals, well, two sets of goals corresponding of the two possible ways to instantiate this. The two possible ways to actually get this, which is my original goal. Right. In intuitive terms, what does that mean here? My hand is here, and the sphere is here. What do I want? I want this to do this, right? This will obviously fail. And the other one is the sphere is here, and I want the hand to move here. This is better. But see, at this point, the system keeps both alternatives, right? So we will see that this will give will trigger the creation of more and more goals, you know, and eventually this to have this move here will match this guy here, just in the same way that we try to match the initial conditions. So this will match. So this will try to execute, but since we have a precondition here, which is not matched here because this is not a hand, so this cannot move on its own, this goal here will fail. Failure. Fail. Right? But this, on the other hand, with the same thing here, will succeed. See? This, so hand should be at the position here. I deduce the previous one, well, I deduce the argument of the command here with this equation there. The precondition is matched here. The hand is, well, H is actually a hand. So then I will be able to issue this move here, right? So here, because of that, here, I can issue a command move. Move of how much here? Alors, we have the initial conditions that tell us that the desire, so yes, is in fact, so the delta here is 25. So move hand by 25. Right? But unfortunately, what the device driver can do is only 10. So in fact here, I will ask it to move by 25, but this poor guy is only able to move by 10, and that's why I need an efferent copy to say 10 and not 25. You see? So here we get an efferent, well, an additional input that will tell me the actual move. So in fact, if the initial, so the hand was here, the sphere is there, and it should go there, right? So I want to move it in one shot from here to there, and it's too far. What I will achieve is only this, here. Okay? It means that at some point, this goal here will still not be satisfied after the first move. And this goal will still be active. So the chaining will still be the same. And then I will output a command of move 15, still move by 10, and I will be there. Goal still not satisfied. I compute the delta between the current position here, and it's 5. And then it does actually 5, and I get 5 here. And I observe that the hand is actually here. The goal here is satisfied, right? And so on. But before doing the so-called so on part, remember that the hand is still holding this. Huh? So, what would make the system think of releasing the thing in order to grab another thing? Well, it all comes from the initial goal there. Because this initial goal there came from here. The first goal is to have this guy from here to here. And in order to have this guy from here to here, we have seen that the hand, well, that the state S2 must be achieved. And S2 is this. It means in fact that the hand and the sphere should be at the same place. And we just achieved it, right? But also that the hand is attached to the sphere. And so far, it is not the case. What is attached to the sphere is this thing. So now this is done. This is done, but this is not done, right? So now I have, well, as I did this, simultaneously, you see, I also had another goal, which is G6, which is in fact the hand should be attached to the sphere. This is a goal that goes in parallel with all of those things, and that's why it's really hard to explain it, because speech is sequential, so we have to, well, to artificially dismember things. Okay. Anyway, so what I want is, so what was the condition? Yes, the hand is attached to this thing, huh? but not that thing. Okay, so what is the right-left term that matched the attachment? We have this. See? It means in fact that if I want the hand to be attached to the sphere, I should aim at not releasing the hand, provided the hand is already attached to the sphere. Okay, this doesn't make any sense, because as of now, the hand is not attached to the sphere. So this is not true. So this will prevent the execution of that. This will not work. What else? Here we have a more direct case. If I want the hand attached to the sphere, I should grab it. But in order to grab it, I must ensure this guy here. I must ensure that hand is at the same place as the sphere, which is true. Hand is not attached to the sphere. I don't know. I don't have such an input. What I know is the hand is attached to this thing. But I have not seen it is not attached to this thing. See, it's a subtlety, but it exists. Okay. So, what I have instead is this thing here, is that this is not true for the sphere, right? But it is true for that thing. And if I want things not to be attached, which is in fact my goal here, then according to this, I have to release whatever I already hold. And this whatever I already hold is true because it is here, and this whatever is this thing. So this allows that to execute. So the command will be sent, and the hand will do this. Remember, this is done concurrently to that move here. So in fact, it turns out that depending on the scheduling in this example only, maybe the release command will be done here. And in fact, what you might see is it is actually this. See? Because we didn't say anything about when before or during we want the thing to be dropped. We let the system think about it. So with no further constraint, he will do it as soon as he can. So thanks to this guy here, at this point here, when the hand is at the position PS0, the sphere is at PS0, and the sphere is not attached, the hand is not attached to the sphere, that's what we get at this point in time here. And this actually matches that. Right? So this allows this model to execute. And this is lucky because actually we had this goal here, and this goal was actually computed here. We wanted from the beginning the hand to be attached to S, in fact. And so far we failed because it was attached to something else. But now we succeeded in releasing it. So now this goal can be achieved by this guy here, grab. So here now the hands holds S, right? The hand is actually attached to S. Remember what we wanted at the very first time was that thing here. We wanted this in order that when we move the hand, the thing that was attached to it, sphere, would move in the same way. And what is S2? S2 is actually what we just got here. Hand and sphere, the same place, and they are both attached here. So now, from now on, this precondition here is met. So now I can fire this M6. It means, in fact, that now I will have the goal G7, which will be fire IM0 with H. What is the position of the hand now? It's PS0. Yes, I don't care about the timings. Yes. What is the delta that I need? Where do I want the hand? I want it at the position P1 here, which was in fact the final position of the sphere, which is in fact PS1. So in fact here it's PS1 minus the position, the initial one, PS0, which is in fact, how much is it? 15. What? Yes. And the final position, which is PS1, and some timings we don't care. So this being a goal, it means in fact run this. But in order to run this, I have to ensure this. Do I have this? Yes, because the hand is at a position is still a hand. So I can run that with the parameters here. So I will have a move. And 15. Same case as here. 15 is bigger than 10, so it will be only 10, and I will get 10 here. So the move now will be doing 2 steps. And the goal will be achieved. Okay, are you still alive? You know, in order to follow this, one has to be very methodical and do it maybe as the machine does it. You know, you have a list of things and you have a list of inputs. Methodically, see where things match. What are the preconditions? You derive your sub-goal, check with your inputs. Does it match or not? Not. Okay, you can solve the goal. The goal is still active, but not now. And you try another one. And as long as you find an entry point, you know. Do you have questions?
another goal and you find the same way.
Uh-huh.
So then you will extract them into a black box.
Yes, yes. Here, what I didn't talk about is I didn't assume another brain in the first brain, but it's really easy because all of those sub-galling actually will give birth to instances of the mothers that made them. You know, so it means in fact that if we had another system that looks at those guys here, not at the mothers but at the coupling, like when I get this goal here, then I got this goal here that was achieved, then I got this goal here that was achieved, then that goal here that was achieved, and again, and again. No, this is simple actually. This is followed by this. It means in fact that when I get a goal like this, it entails the system to issue this thing. When it has been done, we observe that it is always followed by this thing. And this is always followed by the success of that thing here. So this is one model. I will call it MI. This is another one, MJ, MK, and ML. Those models are actually transversal because in fact they don't care about the actual inputs of the world, they care about the execution of those guys here. So in fact we do have a list. When you have this goal, do this, and you will succeed. This is a plan. And when we'll have time, we'll summon the C++ compiler and implement those guys in a black box. Yep.
So another question may be very stupid. Now you know how to release something in your hand and grab another one.
Mm-hmm.
But here is a goal that you want to achieve is now I have the food and there is shoe that I'm wearing, but I want to get it rid of this one and to wear the other one over there. So the system will learn there's a pattern there and we can do the same task.
Well, depends. Yes, but if the ways to do it are actually involving those guys here, and grab and release, you know.
So you mean the system have to think about obviously the possible way, and then you can check if there is a existing successful.
That is right, because in fact this, let's take this example. So, this is one example that the system knows for how to achieve this. But maybe it will learn in subsequent phases or being taught that a magnet on metallic stuff does the same trick. But it is not by virtue of that, it's by virtue of something else. Still, while having the same goal, it might figure out that this is not longer appropriate because this is not met, but maybe the magnetic stuff will be met here by means of a precondition and will be allowed to fire. Anything else? Okay. Well, thank you for your attention. And sure, some of you have further questions. questions or want to discuss, in fact, any topic that you'd like, we'll be available, Chris and myself, from 5 o'clock to 7, we said? Okay. In the other room.
Over in the other building. So in about 20 minutes or so we'll be over there. I would like to ask you, if you have some questions, it would be great to ask them now, even if you think they're silly. Because at 5, we have someone coming over, so in 9 minutes, hopefully no later than that, we'll have someone come over to take photos of us all. So it'd be nice to get at least the people here in the room on RAM. You can say on film. And